Hello guys. So as you know that the electrical drive is a key subsystem of an HEV or EV system. The term electric drive is used for the traction motors and the associated power electronics and the control that ensures our desired motor performance. In this video, we will start by considering some of the DC motor that could be a good candidates for traction motor and explore their behavior and characteristics. So there are several types of DC motors. The simplest one is the permanent magnet DC motor. So we will start with that. So today this video is basically to design a system uh, of DC motor and its controller unit using PID controller. So we are going to design this model today. So before starting, let's open our MATLAB window. So I have already opened our MATLAB window. So to open a new Simulink blank window, we can simply click here, or there is a shortcut, or we can say as a command, we can run it in our command window. So the command is ssc underscore new. So if we run this, so a blank window will open for Simulink modeling. So we will use this. Okay. So if we can search all the required blocks from this library browser. If we click here, we will see that there are several libraries are available. So from there, we can simply go to this Simscape library, and here we can click this rotational actuators, or we can click here in the electrical subsystem. Under electrical subsystem, we can choose this actuators and drivers, this option. So I'm not able to find, I think it is, okay, let me check. So here I think I will be able to find it. So here you can see there are several motors are available. So I'm not using these things. I will simply use a simple DC motor. So to get that, you can search here as well, writing DC motor, or what we can do here, I have find DC motor, or we can simply double click here and search DC motor. So we will get that. So I'm taking from here only. So I have just copied it. So as you can see, I have copied it. Now I will connect it with a voltage source. So I will set the parameters later. Once I connected all the components with this DC motor, I will set the parameters. So what we can do, we can take a controlled voltage source. So we can type this one, this control voltage source, and we can connect this positive terminal to positive and this negative one to negative. Then, so if we open this, in the description part, we can read that when the positive current flows from the electrical positive to negative ports, a positive torque acts the mechanical C to R ports. Motor torque direction can be changed by altering the sign. So we are not here to change the sign here. So what we will do, this R port is for the output of the motor, and the C is the reference. So what we can do, we can take a mechanical rotational reference and we can connect this C port here. Then, so as we are using a Simscape block, so it is mandatory to use a solver configuration in any of the components. So I am just connecting it here. So solver configuration, you can search it here as well. Solver configuration you will get, or otherwise when I open that ssc underscore new tab of Simulink model, so I by default I got that, so I am taking that one. Now also to uh, ground it, I will take an electrical reference. So I will search here and I will get that electrical reference. I will connect it with it. So I have connected. Now I will search here for speed sensor. So to take the speed sensor, I will fetch a block that called ideal rotational motion sensor. You can search it here. So this one I will take. I will simply connect it here. Then this C port, I will connect it with this mechanical rotational reference. I am just copying it and I will connect it here. This W is our output to see the speed of the motor. So I'm just rotating this block. Okay, so I have rotated, and here what I will do, I will connect one PS to Simulink converter. Here you can see PS to Simulink converter. So as I required to observe the speed, so I'm just copying this. Or otherwise, what you can do, you can just search it for PS Simulink converter and as well as a scope block to observe the behavior. So you will get here. So I'm not taking this by default. What is given, I'm just taking that one only. So just copying it and I will connect it here. So all the Simscape blocks, what we will use, will supply a physical signal that is called PS, and to convert into Simulink format, we need a block that is called PS to Simulink converter. Also, there is a reverse block as well. You can see here Simulink to PS converter. Whenever I require that, I have to use this as well. So for now, this is required, so I have used this one. So I have connected this one to observe our speed. Now I need to observe the current. So I need a current measurement block. So what I can do here, I am just putting this under a subsystem. So I have put it in under a subsystem. So this connection port is not required. I will not connect it. Okay, let me open here. So by default here, one connection port is open. I'm just deleting this. I don't require it actually. So I'm just deleted it, and here I will name it as speed sensor. I have named it as speed sensor. Then I need a current measurement block as a current sensor. So I will search for current sensor. So I have got one current sensor that is found under foundation library. I will take this one. Just remove this connection. We'll connect it here, this positive with this positive source and negative with this. So as ammeter is need to be connected in parallel, so I'm just connecting it. Okay. Now I need this PS to Simulink converter. I will take it. So I'm just connecting it. So sorry, actually I told one thing wrong. Actually, ammeter need to be connected in series. So I have connected in series only. You can see here positive with negative terminal. You can see here. So I have connected this one to observe our current behavior. Also, I'm just copying the scope block to connect here. So I have connected it here to observe our current characteristics. Now, what I need to do, so I have connected these ports. Okay. So now I need to set the parameters for this. So here all the ports which I have used by default the parameters is set. Only thing I need to set the parameter for DC motor. So in the settings option, if I go in the settings option, here you will find two options like electrical torque and mechanical torque. So I need to set some parameters in the electrical as well as in some mechanical things I need to change. So here I will keep these two as it is. So it is permanent magnet DC motor. You can see here. In armature resistance, I will change it to 1 ohm. Then in armature inductance, I will set it to 1. So it was by default 12 into 10 to the power minus 6. So I will just make it 1 into 10 to the power minus 6. Okay. So I will just make it this one 1 into 10 to the power minus 6 Henry. Then this, so here we can see it is showing specify back EMF constant. So we will set it to specify torque constant. You can see here I have changed, and now here I will change the uh, parameter. I will set it to 0.1. The unit is Newton meter per amps. Okay. So I have set it the parameters for electrical reference. Now I will set the parameter for mechanical reference. So if I came to the mechanical option, the rotor inertia is 0.01. This I will just change it to kg meter square. I have changed this. This rotor damping, I will change it parameters to 0.001 Newton meter rad per second. So to change it, I will set to this one Newton meter to rad per second. Newton meter divided by rad per second. And this speed that will came out of this port, what we will see in our scope, that is in unit of RPM, a revolution per minute. Okay, so I have set it the parameters. I will simply close these blocks. So now what I need to make, so okay, so for now just make this a subsystem. I'm just making this one subsystem. Okay, so just for now, just extend the extend its connection length. I will just make it a subsystem, and just let me maximize in size. Okay, so here I can see one connection port is showing. So this connection. So I require this. So what we can do here, as we need to supply the voltage. So the supplying voltage will be in Simulink block. So I need to convert that from Simulink to physical signal. So I will use one block that is called physical Simulink to physical signal converter. This one. I will connect it here. And here I will just connect one port, or I can just leave it blank. Okay, let me connect one port here, just input port. So if I write in, I will get this port. So I will connect this port here. So I have connected this one. You can see input port is showing here. So this output one is nothing but our speed. I'm just naming it the speed. And this one is nothing but our current. Just naming it as current. Just change it to current. Just go back. Here I'm just sorting this. Just make sort this connections. Name it to like current observation. And this one as speed observation. So as you can see, our motor permanent magnet DC motor modeling is almost ready. So we need to give some voltage source here. And according to that, we need to set a control strategy. So for that, what we will do, we'll simply search for a step that will be our voltage source. So you can find here step. In step, what we will do, we will just change the parameter, like this final value we will change to 10. So what does it mean? The step input setting, the step input settings is basically like it will go after 10, go to 10 after 1 second. So that means the voltage will be 10 volt after 1 second. So I have set it that I will keep this on, turn on. I will simply click it, apply, and then OK. Now I need to check for one add block. So I will search here add block. Just got this one add block. I will just change the sign a little bit. So the last sign I will change it to negative, and I will connect it here. So this one is connected. So as you know, this one is our speed observation. I need to feedback it. So I will, okay, let me first take the controller first. So for controlling, we will use this PID controller. So we can see the PID controller here. Okay. So we can keep the value what is by default, but to improve the performance of the system of the controller, what we can do, we can change the proportional constant value to 20, and this integral value as 1 as it is. We can just change this one only, proportional constant value, and we'll click apply and then OK. Now we will simply connect it here, and to give the feedback, what I will do, I will simply connect this port here, and to check what will be our actual desired speed from here, and to get the actual speed, I will connect it here. So what I can do, I can connect it here, connect it here. I will connect it here in the speed observation. So once I connect this here, you can see the port number will be changed to 2. In file option, if you go here under this number of ports, it will set it to 2, or you can manually change it to 2, and after that you can connect it. So I have done this things. Before running this model, I need to change the solver configuration. So if we keep the automatic solver configuration, so it will take time. So for that, we will simply go under this modeling option. Here, in this model setting option, we will click here. And it is opened. So here under solver, you can see solver selection, and solver is set it already in automatic solver selection. So we'll change it to OD15S stiff NDF, this option, to make it faster. I just click OK. Once I click OK, I need to save this file. So I will go here in this save option, and I will click here, just name it like DC motor underscore DIY. So I have just changed this name. So this model is saved. You can see here already it is showing ready option. So I can simply run this. So if I click here, so here the time we will keep at 10 seconds. You can see here, I've just run it. Now it got run. So if we open the speed observation, we can see here, this is the speed observation. If we closely look at, we will see. So let me select here and here. So this blue line is our actual speed, what we are receiving using this PID controller. And this speed, this yellow line is the desired speed. So once the controller is controlling the speed of the motor, it is just following the actual desired speed, and it is like that. So this is our speed. You can see. Okay. If I just close this and go here under this current observation, we can see okay. So here we can see here, if the current is from 0, it started and it goes to 200 amps, almost 200 amps, then it comes to 0. But actually it's not 0. Here you can see you can see it's not almost 0, it's some near about 0. So what is the thing? If the armature current is tracked, it shows a this sub spike at 1 second, where the speed change happens. Actually, you once you see the speed observation, in this point the speed change happens. That's why the sub spike is nothing but the case goes here up to 200 amps, and this could be unacceptable in a given situation, such spikes. So in this point, this motor is drawing maximum current. That's why it is going up to 200 amps. And after that, when it reaches to the desired speed, it just come to near about this value. So by this, you can design your DC motor control using PID controller. So as a standard approach to reduce this current spike, so what you have seen here under this here, this current spike is to reduce this, we can use a multi-level controller, also called a cascaded controller. So for a two-level cascaded controller, two controller blocks are used. So here we have used only a single step block, step input, a single PID controller, but there we will cascade two PID controller in series. So the outer one is for speed control, and then the inner one will be for current control. So for this control strategy to work two signals, the speed and the current, we will see what we can do. So what we can do here, we can just make this shift this a little left actually. Now we just name it okay, just name it as, so now we are going to design one cascaded speed controller for this DC motor. So to name it, I will name it like So it is just measuring this desired speed and the actual speed. So I will name it as speed error, and this one as speed controller. Okay, I can keep the name as PID controller. So I will just change here speed PID controller. Then just let me disconnect this for now. Here we just will copy this one here also. I will connect it this port, this PID output port with the speed controller, speed error measurement, this things blocked, and I will just name it. It will be not used for speed error measuring. It will be used for current error measuring. So I will just name it as current error. So I have connected this one. I need to take another PID controller. So to take that, what I will do, I will search for PID controller, or I can simply copy it, but I will search here for a PID controller. So this one I have copied here. You can see. Now I will just connect this port here. Then to measure the current error, what I will do, I will simply connect this to current port. So you can see here current port is there. So I will just make one connection. I will connect it here. So it will just give the feedback of the current. And based on that, it will regulate the current as well. So under this PID controller, I need to change some values. Like previously for speed controller, the proportional value was 20. But in this case, for current control, the proportional constant value, I will set to 0.3. And this integral constant value, I will set for 0.125. So once I have set it, I will click apply. I will click OK. I will simply click the run button. So it is showing some switch to auto elliptic loop configuration. Okay, I will just click it fix. So once it is fixed, I will just run it again. It got run actually. So if I open this current observation now, so previously the spike was up to almost 200 amps, but now using this cascaded PID controller for controlling the current value as well, I have reduced it to almost 48, we can say 48 amps. You can see here. But if we go in the speed observation, the speed observation will be remain same. It is remained same actually. So that's how we can control a DC motor, permanent magnet DC motor, using PID controller, where we can control its speed and as well as its current value. So basically the first one was for a simple PID controller using for controlling the speed. But after that, once I use two PID controller connected in series, I have just first one, this one is for controlling the speed and this one is for controlling the current value, to measure the current value, and based on that, it will feedback the current value. So thank you.